Can you hear me? Hello? Hello?
Yes, sir.
Yes, sir.
Can you
Yes.
see the screen?
Yes, sir.
Yes.
Okay. Well, okay. First of all, from next time now, I will start from this because I find that from from bit late from 11:50 the Microsoft team here gets busy, and I have trouble in logging in. So next from next time I will start from this time. Now let me talk about Lindelof again. So X tau is Lindelof. You can do it for any subset also. Every open cover X has a countable subcover. That means it may be finite, it may be countable infinite. Okay, so that first thing, every compact space is Lindelof. But not the other way. It's stronger. Okay, like we'll see that this is Lindelof, but not compact, because in a metric space we have seen that second countable, Lindelof and separable, they are all equivalent, but not compact. Okay, so it's stronger condition, compactness. Lindelof is weaker. Okay, now look, what we prove that the result, that we call the result. If X tau is second countable, then A X tau. This I proved last time. This is Lindelof. Make sure you read the proof of this, how we are doing it. And P, this I did before minor. X tau is separable. Okay. But now the other way, like here, I have given one example in the node, another example is the Morse plane. Not Morse plane. It is separable, not second countable. What will you do that? Not Morse plane. Morse plane maybe I think second countable. Hmm? So, well, what is the counter example? Just tell me that. Other way. Example. Says, I have given you the example, surgeon feline. It is separable but not second countable. That is another reason to show proof that surgeon feline is not metrizable. Okay. And okay, Lindelof not second countable. That I said R. Because reason is, okay, this is the result that I want to give another proof. If X tau, if rather you can write T. X T is a metric space. That means topology will be generated by D. The following are equivalent. Xt is second countable. Xt is Lindelof. C Xt is separable. Look, Xt is second countable separable, that I proved before. And last time what I said, second countable implies always Lindelof, and for this I gave the proof. Okay, straight proof with the cover on that. Given a cover, I produced a countable subcover, but I can give a proof here. Lindelof metric space is separable, but then that means I can prove the straight the circle. A implies B from here, and B implies C. I will prove, and C implies A proved before. Okay. Now look, C implies A. That means I want to prove this. Every Lindelof metric space is separable. Look, this proof should be easy now because you'll have to recall the proof. Look, before I proved if a metric space xt is anyway compact is totally bounded, it's compact, but you can go straight. is compact or totally bounded, then Xt is separable. Any compact matrix space is totally bounded. But even then you go straight for the proof. So let us recall the proof of that. Suppose Xt is totally bounded. Because given any r greater than 0, positive r, you can get finite number of balls with radius r which will cover whole x. Okay, totally bounded, suppose. So take 1 by n r equal to. Since x is totally bounded, there exists a finite subset that I'm calling Fn of x such that x equal to union px 1 by n. X belongs to Fn. Finite number of balls with radius r will cover x since x is totally bounded. Okay, so you are getting Fn. Now take f equal to union Fn. Okay, look, this is each Fn is finite, so countable union of finite sets is countable. So f is countable. Now you should prove it. I am not giving the proof again. That show that f bar equal to x. So f is countable, so x is separable. Okay, right? This is what you are doing. For compact, how will you do it? Well, compact same thing you'll do, but a little bit one more line extra. Suppose xt is compact. That I told you, number of techniques is quite limited. That's why you need to learn the techniques. Xt is compact. So first take it kind of 1 by n. Now you have to do one more step. That totally bounded immediately you get. But compactness you'll have to do this. Look, p x 1 by n, x belongs to x. For each x we are doing this. This is an open cover of x. Since this is compact and this is your index set here. So there exists a finite set subset Fn of x such that will cover, that means this. Okay. For totally bounded, you are getting straight. For compactness, you'll have to do that. And now take f equal to union of Fn. Now the rest of the proof will be similar to that, what are totally bounded. So this is countable union of finite. So this f is dense in x. This proof will be similar, only this line will be different. Now suppose you have this thing, Lindelof, what will happen? Still you have cover, but now we will get countable subset because of the definition that countable may be finite, may be countable infinite. Okay, such that. But now look here, countable union of countable set is again countable. So f will be countable. I need countable sets. So again this will work. This will be countable. So proof for every compact matrix space is separable and Lindelof, they're essentially same. Only the word instead of finite you will be using countable. Here, only one place countable, nowhere else. That countable set. That's the proof. So every Lindelof metric space is separable. Make sure you complete the proof. Okay. So that now look, we after this compact, we got, this is called a weaker concept of compactness, the Lindelof. Okay. So R, remember that the metric space everything is equivalent. So since this is separable, so this is Lindelof, but this is not compact. So here is an example. This is Lindelof, but not compact. Now look here, compactness definition. Every open cover has a finite subcover for compactness. For Lindelof, every open cover has a countable subcover. Now suppose I want to mix up compact Lindelof. What I want to mix up? So I want to mix up like this. Here I'm bringing the countable. Every countable open cover, not any open cover, every countable open cover has a finite subcover. It happens, I will tell you. It happens often, particularly in metric space. This finite, I am keeping it here. And instead of every open cover, I am taking every countable open cover as a finite subcover. Every countable open cover as a finite subcover. So here it may happen. So let X tau be a topological space. Suppose every countable open cover of X has a finite subcover. Then X tau is called, look, it is weaker than compact. I am not saying every open cover, only countable open cover. So I need to have an adjective. It's called countably compact. I won't go into the details of countably compact other compactness, but I'm just giving you them so that you at least you know their names and that you are familiar with the word. Is countably compact. Okay. So this is called countably compact. Right. So then extra is called countably compact. Okay. That means, let me write again. Definition I'm writing. A topological space X tau is called countably compact if every countable means finite or countable infinite. Countable open cover of X tau has a finite subcover. This. Now look, immediately you can see that. Suppose now I have both countably compact plus Lindelof. Well, before that I should mention every compact space is incountably compact. Every compact space is countably compact. But a countably compact space need not be, that I am going to tell you, is countably compact. It's from the definition from the way. Here every countable cover, open cover you are taking for compact, every open cover. So every compact space is countably compact, but the convert need not be true. So that I am going to explain. Now suppose countably compact plus Lindelof. Now look, start with any open cover. Any open cover. This Lindelof has a countable subcover. That means obviously will be open. In two steps it. But countably compact. Every countable open cover has a finite subcover. Now we have got it. This has a finite subcover. Because this is countably compact. For Lindelof, first any open cover you are reducing to a countable cover, and then by applying countably compact you are reducing to a finite subcover. That means you are getting every open cover as a finite subcover. That means what you are getting, countably compact plus Lindelof is compact. But any compact subset is also countably compact, and before I showed that Lindelof, that means what I am getting? I am getting this result. But that result tells you that some counter example of that result. A topological space is compact if and only if it is both countably compact and Lindelof. Okay. Here you see that R, these, since this is separable, it is metric space, this is Lindelof, but this is not compact. So it is not countably compact. In fact, what I did last semester, you can look at the note, I will show you that in metric space, compact, countably compact, they are same. Okay, they will be same as that. Because a metric space, that I will show you that because a compact metric space is separable, so it will be Lindelof. Okay, right. So that I'll show later on. That is not countably compact. Okay. Now every compact space is countably compact, but a countably compact space need not be Lindelof. Right now, this example, compact, sorry, every countable compact space need not be compact. I will hold it for a while. That will need to know about the ordinals. Okay. So, but there is such a thing that there exists a countably compact space which is not compact, good space actually. Well, so this you got that a topological space compact if and only if it is both countably compact and Lindelof. Okay. Now the thing is, this is fine. But I said in a metric space, countably compact, the same is this. So that what actually we did for metric space, we didn't do that. But this can be proved. I'll give you a proof in a node. I will place it that. But you can think that. Willard has given exercise here. Let me tell you. He had called it cluster point. Actually, it's the same as accumulation point. This is the result we learned. Page 125, 17 F 2. Here he is using the word cluster point. Actually, that means accumulation point. It's the same as accumulation point. Here he is saying that a T1 space, this is very vital, is countably compact, a T1 space. If and only if you can say I've given 2, you can give 1, C1. Okay. If and only if every, but I need basically this thing. Every infinite T1 space X star. Every infinite subset of X has an accumulation point. Look at my notes that I proved. A lot of things I did last semester for the metric space. Metric space I have shown that a subset is compact if every infinite subset of that, instead of X I have taken subset, that is fine, has an accumulation point. So that in a metric space, countably compact is same thing. And that I proved equivalent to compactness. This I proved equivalent to compactness. So that, but a metric space is Q1 space. So that it is in metric space countably compact and compact same thing. So this one I will give the result. I will give the proof. In the meanwhile, you can try that how to prove that. You can take help from the book on the net, but I will post it sometime. Okay, T1 space is countably compact if and only if every infinite subset has an accumulation point. Okay, right? My goal is to what I did for metric space, that I want to tell you that actually in metric space various kinds of compactness they coincide. Anyway, here I should tell you that some authors they take it as a definition. If you have this, every infinite subset of X as an accumulation point, they call it Bolzano-Weierstrass compactness. Or BW compact. They give it a name. I'm just giving you that so that somewhere if you find, then you should understand this. If every infinite subset of a Kx as an accumulation point, people call it BW compact. That means on a T1 space, this result is saying on a T1 space, countable compactness and BW compactness, they're same. And that is the reason I say minimum we actually assume a topological space to be house drop. So particularly we assume T1, so it will coincide with countably compact. But countably compact in terms of cover, it is much easier to understand. Compactness, any type of compactness, you should have in terms of the cover first. Okay, so that this is due, this I will do. But here, but you remember that in metric space you have done another thing in terms of the sequence. That if you have this, then A is compact. Remember that in xt, if and only if every sequence xn in A has a subsequence xnk, since every compact subset in Hausdorff will have to be closed, so its limit should be also in A, converging to a point X in A. That means every sequence has a convergent subsequence with limit in the set itself. That every sequence has a convergent subsequence. But look, whether it is metric space or not, I can take it as a characterization of space of that. So that here is a definition. Okay, Willard is saying given 17G, that is page 125. 17G, that is saying a topological space X tau is called, because we are doing in sequence, it's called sequentially compact. Since instead of A I have taken X, so that if every sequence in X, if every, here X is, I am taking whole things, so I don't need to bother about it. It will be inside X. If every sequence xn in X has a convergent subsequence. But be careful. If you are taking on a subset, then you'll have to say convergent subsequence with limit converging to a point x in A. Okay. Because you need to ensure that it sequentially compact. So that look, in metric space I have proved this is equivalent to compactness. So that in metric space I have proved basically countable compact, sequential compact, so that this I proved result. Let xt be a metric space and actually you can take infinite subsets. This, the following are equivalent. A is compact in X with xt. B is countably compact in xt. Is sequentially compact. In fact, people while working with metric space, they prefer to work with this. This is called the sequential characterization. Of compact subsets in a metric space. That's why it's very important. Usually when you work in a metric space, if you can do it, you should use this thing, sequential characterization. Okay. Here, I'm just leaving it an exercise on that. If you can do it, it's fine. But if you can't do, then it's also fine. So this is the thing Willard is saying 17G1. Two. Okay. First is saying that not G1 every, actually usually there is no link between sequentially compact and countably compact. Not every sequentially, so that you'll have to find a non-metralizable space. Then you can think of the not every sequentially compact space. Sorry, first thing. Not every compact space is sequentially compact. Okay, and G2 is saying this. Every sequentially compact space, this is what that you should think of. Every sequentially compact space, this proof should not be difficult. Sequentially compact space is countably compact. You have to show that every countable open cover has a finite subcover. Okay. So if you do not have it, you can construct a sequence which won't have any convergent subsequence. Yes. Every sequentially compact, but here, this other way, not every sequentially compact space is sequentially compact space is compact. This he has put in here. Reason is, if you can find a sequentially compact space, that has to be countably compact. But if it is not compact, a countably compact, which is as well sequentially compact but not compact, then it will work. Okay. So these and this plus, it is saying that there is, he's saying that sequential compactness is neither weaker than compactness nor stronger than compactness. That means sequential compactness and the compactness, you can't link them in YAL. In YAL you can't link them. Sequential compactness and compactness, okay, you can't link them. Okay. Now G3 is saying, G3 is saying, sorry. You see there is a link with that. A first countable space, these are all optional things. But if you try, at least even if you don't get the solution complete, still you get some better ideas about it. A first countable space is sequentially compact if and only if it is countably compact. Look, every metric space is first countable. That is another reason here. Sequential compactness and countable compactness will be the same in a metric space. And if you can work out, you'll see that here first countable means you have sequential characterization of closed sets. That helps actually. Here in first countable space, you have all the sequential characterizations which are available in metric space, and that helps. So in the first countable space, it is sequentially compact if and only if it is countably compact. Okay, that result that I told you, I will prove it. A T1 space is countably compact if and only if every infinite subset has an accumulation point. So that I'll do. So this much is fine with you. That, okay, you think of that. Okay, so this much will be fine with countably compact, sequential compact. I just gave you the ideas on that. Okay, so that you know that. Okay, so that I will देखता हूँ, चलो, so that I do. So this, the rest of the note you should read. here I should tell you that mention, make sure the metric space page starting from page 166. So basically in that note, what I did last semester, you should make sure that I am not going to teach you again. You must read again and go through the proof carefully. You don't need to mug up. Okay. Because I will take the major exam on online, you will have access to everything. Okay. So that, look here in page 160, I have given 3 lemmas. So make sure that this is a small result. Pay some attention what I'm trying to say. Actually lemmas, 4 lemmas, 5.4. Okay. 5.4 is every compact subset is totally bounded. Okay. Oh, there is another thing that this is basically a proved in YAL that every compact metric space is separable. 5.5. Every compact metric space is separable. Okay. And here, this proposition 5.8. Look how I am doing it. If I have taken a metric space here, I am doing everything in a metric space, and I have taken a sequence of distinct points. Sequence of distinct points means xn not equal to xm whenever n not equal to n. Distinct points. Okay, and you take this set, the collection of the members of that set. Each has an accumulation point, so this will be an infinite set. Okay, so in a metric space, accumulation point, it has to be infinite subset. Okay, finite subset doesn't have any accumulation point in a metric space. Because in a T1 space, you have accumulation point, every neighborhood intersects infinitely many points. Okay, right? Then there exists a subsequence converging to this. This actually is telling you what? This is actually telling you that every, look, that there exists a subsequence converging to a point x. Okay, if it is accumulation point. Okay, right? So that this is actually saying in a metric space, oh, it was 100 other. Okay. Look, proposition 5.8. Actually, it is saying what? Okay, right? Sequence of, so suppose you start with a metric space and you have infinite subset. Okay, right. I like to show that it has an accumulation point. Okay, look here, go by this. Okay, infinite subset. Okay, so that we are doing this a sequence on that. It is showing that every infinite, so that I can always pick up a sequence. Every infinite subset. Look, now take P, B is infinite. If V is infinite, okay, then I can pick up a sequence of distinct points here. Since this is infinite, so I can pick up a sequence of distinct points. Okay, don't confuse with this a sequence of distinct points. Distinct points. I can pick up from here. Okay, right? Right? So what I'm saying, okay, if this is an accumulation point, now look, if this is an accumulation point, this is converging. So okay, this is distinct parts of fine. So assume that hypothesis B has an accumulation point. Well, let me write it differently. What I am going to show that here countable compactness implies sequential compactness. I think I have proved it. Sequential compactness in a metric space. That I want to prove that. Okay, so let me see that whether I have done it. Basically this proposition 5.2, you should look theorem 5.9. That I was trying to tell you. Then I realized that suppose every infinite subset of has an accumulation point in A. Okay, that is basically I proved that metric space theorem. I have not proved. I have mentioned that this is same as countable compactness. Then every sequence in X has a subsequence converging to a point. That means this theorem 5 point says this result, that countable compactness implies sequential compactness in a metric space. So, but that uses proposition 5.8, so that's why I have split into the many things, small results. So proposition 5.8, make sure you should prove. You should read both, read the proof. So why I should read the proof if the theorem doesn't come? Well, I won't give you that theorem in this. But if you read the proof of this, you will get to know the techniques. How I am getting the techniques. So techniques in the proofs are important. So that very likely in the exam, when you see something, then we say, okay, this technique may work. So that's why you need to look at the proof of this theorem 5.8 and 5.9. And finally, I have given that proof. Okay, theorem 5.10. That in a metric space, countable compactness, sequential compactness, they are all same. Okay, so that I split into small results. That's why it looks simpler. Okay, so make sure that after this you should do this. I'm again strongly suggesting that starting from lemma, particularly then proposition 5.8, theorem 5.9 and theorem 5.10. This is the equivalent characterizations of compactness in a metric space. That means in a metric space, countable compactness, sequential compactness, and compactness, they are all same. They are all same. Okay. Sequential compactness is very useful in metric space, but sometimes we use that characterization of countable compactness, that every infinite subset has an accumulation point. That actually you will see that theorem 5.11. Okay, here you get the proof on that. I put the remark on that. Here I should have the remark on that. What is that remark on it? Look, here in theorem 5.11, a metric space, I'm just going to talk about its implications. That basically I tried to say in the remark in page 166. A metric space xt is compact if and only if it is complete and totally bounded. Here, put this attention here. Now look, I have given an exercise in the minor. Look, there actually need to use this thing. You don't need to use it because for not no word dense. This is homeomorphic. That's the thing to this with the usual distance. So this is homeomorphic to any open interval. So homeomorphism, this I mean homeomorphism. Look, this is complete, but this is not complete. But since this is homeomorphic, this means this is completely metrizable. This is also completely metrizable. What does it mean? Metrizable means that is already metrizable, so that's not a big deal. Completely metrizable means you get another metric on here, which will give you the same topology as generated by this, but that will be a complete metric. That means here I get another metric row on that. Which will give me the same topology generated by this. But this is not complete here, but that will be complete. That means, okay, right, got it. So that particularly you see what is happening. That means I am getting two metrics equivalent to each other basically. But one of them is complete, other one is not complete. Okay, but look, this was not compact. But if it is compact, it cannot happen because if you have compact, look, compactness is a topological property. It only depends on the open cover. So if it is compact, it doesn't matter if you take another metric row equivalent to this. Look, you need to once take. If X is compact, then this will be compact if it is equivalent. So by that, X row will be complete. Okay, that means any equivalent metric will be also complete. Any equivalent metric will be complete. That means in a compact metric space, any two equivalent metrics will have to be complete. There is no chance like this that one metric is complete, another metric is incomplete. It is happening because this is not compact. Like the same thing here. This I told you that what actually will be you usually use. Okay, so that a metric space is compact if and only if it is that means from this you are getting what? Any two equivalent metrics on a compact metric space. Any two equivalent metrics in a compact metric space are both complete. So that anomaly is basically happening because R was not compact also. Okay, right. That's the way the minus pi by 2 we are doing that. Okay. Look, R you cannot have Homeomorphic to any closed interval, closed bounded interval, because that is compact. Okay, so it has to be can homeomorphic to an open interval. Okay, are both complete. Here, I am leaving this exercise to you. But if you can't do it, but you can go to the literature on the name. Suppose I say that the other way, that any two metrics on a metric space, on a space set X, any two equivalent metrics on a set X are complete. Both are complete. Okay. That okay, let me write. Then is it compact? Let me write it this way. What I am trying to say. I'm saying question, actually query. Let X star, let me write it, be a topological space, be a metrical space. You can write a metrical space. Suppose any metric D generating tau is complete. That is, whatever metric you get, that already you have in a compact metric space. Any metric has to be generating the topology will have to be complete. But I am asking the question the reverse direction. Is X tau compact? That is my question. Okay. Answer is yes, but it is not easy to prove. It is somebody's research on that. You can think of that. Okay. But the point is that compact metric space behaves very well. Okay. It behaves very well. That's why people are interested in compact metric space. Okay. So that make sure that you do it. That you read all these things that I already told you. And the comment, I'm saying that in page 166. Okay, this will I'll teach you on Monday, but compactness continued at the Heinberg theorem. That let me tell you that something. I'm just telling on Monday. I will teach you this note on that Heinberg. That you should read this note. That I have also uploaded, I think, again. That 167 to 176. That countable compactness, that also I will upload as well. Okay, this much I want to finish it that on the problems. Here, basically I am talking about Heinberg theorem. That is very important. Next semester we will be doing function analysis. There also it will play a big role because finite dimensional nonlinear space. So Heinberg theorem is very important. Okay, so I'll talk about Heinberg theorem again. I'll talk about its proof that I have given last semester, the easy proof on that. That is this there. Okay, so make sure you come to the class after reading this note. That will be easier because I will just review this note. Okay, right? And then I will give you some time. I'll post that the equivalent characterization of countable compactness. But after this, I will next week I'll sit to. Can you tell me when is the mid-semester break? Hello? Hello?
Yes, sir. It's
The
from
26 to
tomorrow.
28.
February or March? Hello?
February,
Yes, sir.
sir.
20 to 28.
26 to 28.
Oh, next week there is no class. No, 28 में what 27, 28 class नहीं है.
No, sir.
Then what will be the next class? 3rd March or something? The 4th March? Huh? Oh, watcha. Somehow I missed the calendar on that. I don't know where it is on that. I couldn't find the mail also on that. Okay. Then the next class you should send me the email to when is the next class or the mid semester break and that. Okay. Anyway, next class I will talk about Hahn-Budel theorem. After that, I'll talk about function space. That means what I had a brief discussion, but I want to do it in detail. What Aliprantis Barkinsa they have done and that. Okay, so uniform convergence, point-wise convergence, Ascoli-Argila theorem, Stone-Basters theorem, I want to teach. After that, I'll go to connectedness. So you send me an email that when is the mid-semester break and that. So in the next class, if it is that means next Friday, okay. If I am not busy, I will take the class. Okay, but my next class it will be Hein-Model theorem. Okay, and I think by then you will get your answer scripts and that. Saurabh has already started grading. Okay, fine. Bye. Okay, see you.